All right, folks, it is Thursday, March 26th, 2020. We're in the second week of the coronavirus quarantine. I hope you guys are all doing well. This is going to be the last lecture for magnetism. I'm going to wrap up this unit here with a couple of very brief concepts here, focused primarily on electromagnetic induction. So the big ideas here are that magnetism can produce an electric current, and we know that current, or a moving charge, also produces magnetism. And let's just make this. So one of the things that we saw, or we have seen experimentally, and I wish we were back at the school, we could test this out, but if you take a magnet and you pass it through a coil of wire, there's no additional voltage source, no battery. Just by moving that magnet back and forth around that coil, you can cause the electrons to move in that wire. This is what we call electromagnetic induction. So as you move that magnet back and forth, the electrons in the wire start moving. Now notice that when in this simulation you can see that when the magnet stops moving, there is no current flow. And so you only induce current when that magnet is moving back and forth. So experimentally we could test this out, and there's a few things that we could change, we could try changing. So in some of the activities that we had designed for you guys, if you change or you move that magnet faster through the coil, you can create more current. If you change the number of coils, the number of turns in the coil, you can also change the amount of voltage or the amount of current induced. The strength of the magnetic field, so if I use a much stronger magnet versus a weaker magnet, that also affects it. And then the last one is the size of the loop, or the area of the loop. And so these four parameters are going to form what we call Faraday's law. And skip ahead to here. Faraday's law is stated this following: the voltage induced is equal to the change in the number of turns, the magnetic field, or the area divided by the change in time. So N refers to the number of coils of wire, just the number of coils. B is the magnetic field measured in Teslas. V is the voltage measured in volts, and then the area is measured in square meters. And all of this is time dependent, divided by the change in time. So when you look this up online, or you look at textbooks around electromagnetic induction, you'll hear this term that they call electromagnetic flux. Electromagnetic flux refers to the amount of magnetic field lines, or the amount of magnetic field that goes through a certain area. And so an actual textbook would show Faraday's law stated as the following. It would say that V is equal to the change in phi divided by the change in T. This funny character phi is the symbol for magnetic flux. Magnetic flux is simply just the magnetic field times the area. It's the amount of magnetic field that goes or gets captured by a closed loop. And so effectively that becomes this same equation. V is equal to delta NBA divided by delta T. So there's a few problems that involve electromagnetic induction that are assigned for you guys. We'll take a look at a couple of those here together. But first, just want to cover two ideas of where this comes into play. So the most relevant one are motors and generators. And so in motors, we have a wire that conducts electricity. And one of the things that we saw is that when we run electricity through a wire, it creates its own magnetic field. And when you run that, or you put that inside a permanent magnet, there's a force, right? So these things have a force applied to them, and that force is going to cause or force the coil to turn. So in real motors, though, this only works to a certain degree, right? Because it will pull it and then it doesn't keep moving. So there are what they call a commutator ring and brushes. And so Let me spin ahead here. So in this diagram here, you'll see that there is what is called a commutator ring. It's split, and then these brushes here make contact with that ring, and that basically turns the coils on and off, and it allows it to basically pull and pull and pull the coil, so that creates a continuous spinning motion in that motor. Electric generators are basically the exact same thing as a motor, but instead of applying electricity to cause it to spin, you are spinning the coil, and by spinning the coil in a permanent magnet, we saw that Faraday's law says that if you are changing or moving that flux, the change in flux will induce an electric current. So those are a couple main ways you might see electromagnetic induction used in the real world. And then the last one, this is a fun one that some of you guys got a chance to see in the activities, but it's called Lenz's law. Effectively what happens is when you take a magnet and you drop it through a conducting cylinder, that induces a current in the cylinder, or in the copper tube, and that copper tube then has an opposing force against the magnet. And so some of you guys saw this. There's a long tube where when you drop the magnet through the tube, it slows down the dropping. So unfortunately we don't get a chance to do this here remotely, but this is what is called Lenz's law. And there's a little diagram here in the upper right that shows kind of what that demo would look like. So that's it for this unit. Here are a bunch of the terms that we introduced here in magnetism. And I'm going to switch over here and we'll take a look at some of those problems that I assigned in electromagnetic induction, and we'll take a look at how we solve those. So switch to this, and let's do that. All right, let's see. That's flipped. That's better. All right, so this assignment, there's only 5 problems to do, and they are all going to use Faraday's law. So Faraday's law stated is the following. So the force, sorry, not the force, the voltage induced is equal to the number of turns times the magnetic field times the area divided by the change in time. And it's actually the change in all of this. All right. And so in this problem here we have a 13 centimeter diameter loop with 13 windings that's pulled through 4.1 Tesla magnetic field in 0.0170 seconds. So I'm just going to convert some of these things. So I've got the diameter is equal to 13 centimeters. I have N is equal to 13 windings. The magnetic field is equal to 4.10 Teslas, and the time, the change in time, is equal to 0.0170 seconds. Now, we can assume that this is a circular loop, and so to find the area, we know that area of a circle is pi r squared. If the diameter is 13 centimeters, then the radius is going to be 6.5 centimeters. And in meters, we have to convert that to meters. So this is going to equal 3.14 times the radius, which is 0.065 meters squared. And then we put that into our calculator. 0.04 times 0.065 squared. We get 0.0133 meters squared. We have the magnetic field B, we have 13 windings, we have T, so now we're ready to solve this. Voltage is equal to 13 windings times the magnetic field, 4.10 Teslas, times the area, which is 0.0133 meters squared, divided by 0.0170 seconds. And so 13 times 4.1 times 0.0133 divided by 0.017 gives me 41.7 volts. So these problems are all very similar to this. Give that a try. If you have any problems, reach out to me, send me an email, and I hope you all are doing well. Talk to you soon. Take care. Bye-bye.